Now let's start chapter 10. In chapter 10, we'll also talk about comparisons, but the difference between this chapter and chapter 9 is now we'll be comparing the measurements, or in other words, the measurements that we compare would be numbers instead of characteristics. So we're comparing numerical data instead of the categorical data. And we'll learn how to understand the distribution of sample means. And then we'll talk about the central limit theorem and test the hypothesis, one sample and two mass sample and two independent samples. And of course, not all these topics will be required for the specific course. And we'll decide the confidence limits and also the effect not knowing the variances. Those are the learning object of chapter 10. Not all of them are required for this specific course. Now, to start with, let's take a look at form measurements. Suppose that this form measurements looks like we have two copies of one copy of two, and then one copy of four. And then what we can calculate by hand very easily is their mean and also their variance. The mean is very simple. So here, the variance or the mean of these measurements would be, we simply add those numbers. So it's 1 plus 2, 1 plus 1 plus 2 plus 4. Whatever the result is I think in this case is 8. And then we divide it by 4 because there are 4 measurements. So we get the mean is equal to 4. What's slightly harder is the variance. And recall that in the last chapter, the variance was calculated by this formula. We have the population variance divided by the sample size times the improvement factor. And of course, we can't expect a neat formula such as p times 1 minus p as we have seen before. However, we do expect that the variance will obey a similar formula like this. So let's start with the mean. The mean is simple. We just add all these measurements and divide by the number of measurements. So in this case, it's 4. And so we add all this together, divide by 4, we get 2. Now, the population variance is, for each of the measurements, we calculate the difference between that measurement and the mean, and then we square it, and we add all those numbers, and then we divide by the total number of measurements. So in this case, our mean is 2, and our measurements are 1, 1, 2, and 2. So if you plug in this formula, you have 1 minus 2 square it, and plus another 1 minus 2 square it, plus 2 minus 2 square root, which is 0, and plus 4 minus 2 square root. And then eventually you divide the total by 4, you get 1.5. And if you need a standard deviation, simply take the square root. All right, so here, let's summarize the formula and for the variance and average of x bar. The average of x bar is equal to mu, the population variance, and the variance is calculated by the following formula. We have two cases. One is with replacement. In that case, the variance of x bar is equal to sigma of x squared, the standard deviation squared, divided by the sample size, n. And if you want to do it without replacement, we have a similar first term, but now we multiply it by our improvement factor, which is big N minus small n times big N minus 1. If you still remember a similar formula from the previous chapter, you see this factor is exactly the same. Now, let's take a look at the sample means for sample of size 2. So let's actually do 2 observations. And so basically, we're taking a sample of size 2 with replacement. So for example, you can possibly take the first measurement as 1, the second one as the same 1, or the second one as a different 1, or the second one as a 2, and the second one as a 4. So here, the circled elements happens because we're doing this with replacement. So if you take the first one and put it back, it is possible that you can take the same element again. Now, if you add all these elements and then divide by 16, you will get the mean. So, and similarly, you can also do the variance. So in this case, the calculation, let's take a look at in our book. This example is in chapter is on page 200 and 268. This example is 268. So let's calculate variance. So the variance, and we can do it in two different calculations. So the first calculation, the variance of x bar, is the direct calculation. So please turn to page 268. I'm going to open a whiteboard to do this. So here, let me just open the whiteboard. And let's do this calculation right here on this whiteboard. So now we have a total of 16 items, and they've been there'll be, look at this here. We have 4 of them being ones, and we also 4 1.5s, and also 4 2.5s, 1 2, 2 3s, and 1 4. So if you do it in our whiteboard, working. Just go to the whiteboard one more time. There we go. Okay, so now let's go to this board, and you see we have the mean, or the mu, is equal to 2, and now we have 4 copies of ones, so we have 4 times 1 minus 2, and then square it, and then plus we also have 4 copies of 1.5s, and minus 2 is square it, and also we have 4 copies of 2.5s, 2.5 minus 2 square it, and now we have also 1 copy of 2, so it's 2 minus 2 squared, and which is 0. And also we have 2 copies of 3, so it's 2 times 3 minus 2 squared. And then finally we have 1 copy of 4, 4 minus 2 squared. So we add all this together, and then we divide the total. We divide the total by 16 because there are 16 combinations. So we get 12 over 16, or in other words, is 3 over 4. And this is the variance of x bar by a direct calculation. On the other hand, the formula will give you a much easier calculation, because the formula basically says if you're doing the sampling without replacement, we simply use the sigma squared of x and then divides by the sample size. So in this case, the sigma squared of x, which is the variance, was calculated just now as 1.5, see the previous slide, and now the population size is 2, so this is 0.75, which is the same thing as 3 over 4. So you see here, we get exactly the same result, but the second calculation using the formula will be much simpler. So I strongly recommend you use this formula to do the calculation. Now, how do we apply this in real life? Well, here, this one example is the sampling inspection. Suppose we're measuring objects whose length is supposed to be exactly 2 centimeters. Now, we allow the standard deviation, and which is about 0.0008 centimeter. And now we sample 4 measurements. And what is the chance that the sample mean x bar is within 0.0010 centimeter of the 2? Or in other words, what is the chance that sample mean is within 2 plus or minus 0.001? Now, in order to answer this question, we calculate the sigma x bar, so the variance of the x bar. So here, this is of course a separate problem. We calculate sigma of x bar, and by the same formula is sigma of x squared and divides by n. So this tells you that sigma squared of, actually without a square, just x bar. If you take the square root of both sides, so you get sigma of x divided by the square root of n. In this case, n is 4, so you can get the standard deviation, which is 0.0008 divided by 2. So this will give you 0.0004. All right, so this is the sigma x bar. Now, what is the chance that the sample mean is within 0.0010? So now the question we want to ask is how many standard deviation away is this? So we'll do the calculation here. So 0.010 divides by this sigma x bar squared, sigma bar x, which is 0.0004, will give you 2.5. Or in other words, we're basically asking what is the probability that this number is within 2.5 standard deviation away? And this can be calculated by this command p norm 2.5 minus p norm of negative 2.5. And the result you obtain is about 0.988. Or in other words, in about 98.8% of the time, this should be the case. So if you observe something else, if you observe something that's different, that probably indicates that there's something wrong with your machine, because that's not very likely. Though it's possible, but it's not likely. And there's also another example. So in the setup described same as above, and if the operator measures lengths and they exceed 2 by 0.0013, 0.0017, 0.0012, and 0.0028. So we can add these four numbers, 0.0013 and plus 0.0017 and plus 0.0012 plus 0.0028. And now we're going to divide this number, and we're going to divide this number by the total, or in other words, it's 0.007 and divided by 4. So the average is about 0.00175, 0.00175. Now the question is, how many standard deviation away? How many standard deviation away is that? Now let's actually do our division. Let's do the division. Let's divide this number. Let's divide this number. And by here, the standard deviation we calculated, which is supposed to be 0.0004. So we get some number that's 4.375. Or in other words, what is the probability? What is the probability that something is beyond 4.305 standard deviation? Well, the answer is that's not very likely at all. In fact, you can use the p norm. You can use this command, p norm, and a 4.375 minus p norm of negative 4.375, and the answer is 0.9999 something. So it's almost 99.999% of the time, the measurement of the mean should be within 4.375 standard deviation away. Or in other words, if you observe that this thing exceeded that boundary, that means extremely likely there's something wrong with the machine. So that is your conclusion. That is your conclusion, because that's really, really unlikely. Now let's take a look at the central limit theorem. The central limit theorem says that if a population of measurement has the mean mu and variance sigma, then if we do a random sample of n measurements, and when n is really, really large, then the probability the sample mean x bar is within the distance z, which is number, times sigma x bar, which is the standard deviation of x bar of mu, is given by the standard normal distribution. And of course, we have the table at the back of the book. So if this sounds confusing to you, just remember this. When you have some very, very large sample size, and then the sample mean will basically follow the standard normal distribution. So, or in other words, if you want to find out, for example, if you have a large sample, then the probability for the sample mean to be within 1.2 standard deviation away will be calculated by this code. And so this code will give you the answer that's approximately 0.77%. I mean 77%. So that is the probability for the sample mean. And if the sample size is large, that's probability for the sample mean to be within 1.2 standard deviation away. All right, we'll look at the next example in the next video. Thank you very much for watching. I will see you in our next video.